Dobar dan svima i dobrodošli na jedno interesantno predavanje koje će nam danas održati naš gost, profesor Andrea Belleri sa Univerziteta iz Bergama, gde je, koliko sam vidio iz njegove biografije, on i rukovodilac studijskog programa vezan za, kažem, inženjerstvo građevinsko i to zgrada. Sad, sama njegova kraća biografija je dostupna, mogli ste pročitati, aktivan je na nekoliko područja, između ostalog na istraživanju u stvari vezanih za efekte diafragmi koje mi vezujemo za neke naše probleme prilikom projektovanja u smislu krutosti tavanica. Kao što znate, uglavnom svi idemo sa tom pretpostavkom da se tavanica ponaša kao kruta diafragma, ali retko kad se ko zapita, a šta ako se ne ponaša. Tako da danas ćemo da čujemo od njega njegovo iskustvo sa tim, ne samo teorijska, nego i eksperimentalno, pošto je bio aktivan na tom polju. Andrea, please, the floor is yours.
Okay, thank you.
Thank you.
Well, good afternoon to everybody. First of all, I would like to thank Professor Marinkovic and Vuko Bratovic for the kind invitation. And I am very pleased to be with you today to talk about the seismic behavior and design of floor diaphragms. First of all, I would like to acknowledge my research group, the research group where I belong to, of structures in Bergamo, which is led by Paolo Riva. Then there is like Alessandra Marini, myself, Chiara Passoni, and Simone Labò, and all the present and former PhD students that make possible like the research. So let's talk today about like four diaphragms. So for diaphragms, in general, we'll need to carry the gravity loads. We need to distribute the horizontal loads like wind loads, inertia loads to the lateral force resisting system. And they need to tie the structure together and impose like displacement compatibility. Regarding like this displacement compatibility, like some transfer forces may arise in addition to inertia loads, particularly in multi-story buildings when we have like setbacks or like the podium diaphragm at the grade level, or anytime we have like different lateral force resisting systems acting together, like a frame or a frame or a wall systems, they have like alone a different deflected shape. When they are forced to move like together, transfer forces arises in the diaphragm. The greater the difference in stiffness, the higher the force transfer. So inertia and transfer forces are linked together because we have like accelerations that will give rise to inertia forces. Then we have like the relative displacement of the lateral force resisting systems, and this may give rise to transfer forces. So another issue related to diaphragms is associated with like its flexibility. Why we are focusing about it? Different building codes provide different formulation to see when a diaphragm is rigid or flexible. So if a diaphragm is rigid, we can like model it as like a rigid floor, and we can lump all the mass and all the rotational inertia at the diaphragm centroid. In the case the diaphragm is flexible, it will behave like a simply supportive beam between the vertical elements of the lateral force resisting system. In general, we see that low-rise buildings and buildings with very stiff vertical elements are more susceptible to floor diaphragm flexibility problems than taller structures. Regarding like the floor diaphragms, we may consider it as like a deep beam inside the building. So they will be subjected to inertia forces, and the inertia forces will make rise to internal actions inside like the diaphragm in terms of like bending moment and the shear loads. So the bending moment will be carried by compression and tension cords at the side of the diaphragm. at the edges of the diaphragm, we will have like that the diaphragm need to distribute the inertial loads to the lateral force resisting system through collectors. Then if we consider like the shear loads, we need to make them carried by the diaphragm, usually in the slab, by providing like a rebar mesh or like a welded wire mesh. In the case of internal beam or beams, we need to make like the shear flow transferring across the internal beam. And we can do that, for instance, like we're considering the shear stresses from available formulation, like the formulation of Juravsky. This is usually the case of continuous slab, but what happens in flows without a continuous slab? So I want to show you two types of systems which have no continuous slab. One is like precast floors, and the other one is a beam and clay block floors. For both these systems, I was honored to be part of like some research project. In the first one, it's called a DSDM project, where it was like tested at the University of California, San Diego in 2008, almost 20 years ago, and was dealing with precast floors. The other one is the Decover project, which was held last December in EU Center in Pavia. So let's talk about the SDM project. This project was head by the scientific guidance of Professor Fleischmann as like a main principal investigator, and in California, University of San Diego, Professor Jose Restrepo was in charge. Basically, it is like a three-story half-scale precast reinforced concrete building resembling a parking garage with 3 stories made with different types of units and only like shear walls at the edges of this system. Shear walls behaving like as rocking walls. So the first floor was made by traditional double T units plus cast-in place topping with the addition of dry assembled shear joints. The second floor unit was made by hollow core units plus cast-in place topping with the addition like of ductile reinforcement across the shear joints between the different units. The third floor was completely pre-topped unit with dry assembled joints both for the shear action and the flexure. So here you can see the shake table test of the maximum considered earthquake which was imposed to the shake table. So you see like the displacement of the diaphragms and the engagement of the rocking walls. The diaphragm was subjected to different sets of input loads. This was like the maximum one in that set of testing. And this is like the recorded like acceleration at the diaphragm level. So on the left-hand side, you can see like in the dashed line, what was like the building code at that time provision of demand of this diaphragm. You can see that is quite lower compared to the actual acceleration demand that happened in the diaphragm. On the right-hand side, you can see like the acceleration intensity along the span of the diaphragm for different earthquake loading. Here you can see like some video of the damage during like the test. You can see on the left-hand side the hollow core units, and on the right-hand side the third floor with like a pre-top unit. You see that in the third floor there was like a failure of the core reinforcement, and this is particularly interesting that happened across like the columns, where there was basically like a stress concentration that happened also like in the second floor. So the floor was like the floor that was damaged was like repaired, and a new core system was provided and was made by traditional reinforcing bars with like friction welded at the ends at steel discs, and then these elements were welded together. Here you can see the damage that happened during the test. On the left-hand side, again, like the second floor, you can see like the opening of the joint that was like developing at the column lines. So that was represented like a weakness of the system. This elongation made like some fracture in the reinforced concrete in the cords in the steel rebars. On the right-hand side, you can see like the damage on the third floor. You can see how also like with this system, like this type of like connection was not suitable for this high seismic demand. Particularly, there was like damage associated and located in the thermically altered region due to welding. So you can see here like the damage at the weld, and both like the weld with this steel slug and also like damage at the weld due to friction welding. So another test was conducted after like an additional repair where they were made like a continuous reinforced concrete curb with like was like designed for shear transfer through shear friction. So the lesson learned from this test was a new diaphragm design methodology. Basically, the first step was like to divide the different connections typologies based on the available deformability. So they were divided into low deformability elements, moderate deformability elements, and high deformability elements. For each of those type of connections, three different design options are available. So for the low seismic zone, an elastic design option with lower ductility elements is possible, where the diaphragm should be like behaving elastic, also both for the life safety limit state and the collapse prevention limit state. Then for increasing seismic intensity, moderate ductility elements can be adopted and a basic design option implemented. In this case, the diaphragm will behave elastically up to the life safety and in a ductile manner in considering the collapse prevention limit state. In this case, some factors are included to avoid like brittle failure and making like flexural applying capacity design, making like a flexure plasticization happening before like a shear failure. Then like for high seismic demand, a reduced design option is available for high ductile elements. And in this case, it's possible to consider the diaphragm plasticization also at the life safety. So it is important to derive for this type of system the actual stiffness of the diaphragm, both in terms of flexure and shear. And this is possible thanks to considering the actual connection implemented in the diaphragm, and through like equation and equilibrium, we can like define an effective elastic modulus and effective shear modulus. This is good for define the right floor acceleration and the right distribution of the seismic forces along the lateral force resisting elements. In addition, the actual strength of the diaphragm needs to be assessed to properly apply the capacity design principles. Another issue is related to the unseating of the floors in some units at higher seismic demand. This happen in this system, but also could happen in moment-resisting frames. In the case due to beam elongation as an effect of plastic hinges. Plastic hinges develop at the end of the beams. The beam elongates and it pushes away the column from the floor. So this situation could like fracture the connections and the rebars. And so there are some regions where the shear transfer is not allowed and some others where it's allowed. So in the design, it should be taken into account. And this is particularly effective like in the New Zealand building code. Then let's talk about another type of diaphragm, the beam and clay block diaphragm that is typical, for instance, in Italy. This research started from a motivation related to the existing building stock, which is quite old and it has like several deficiencies like architectural, energetical, structural, and functional. And also there is this need, urgent need for building stock renovation, also like promoted by the European Union. So how can we deal with this goal? We can either like demolish and reconstruct the buildings, the old buildings, but this will produce a large amount of waste, raw material consumption, and of course the disruption of building functionality. Or we can try to retrofit the existing ones. And to avoid like the inhabitants relocation, which is one of the main barrier to building renovation, solutions have been like developed like as acting only from the outside, like shear walls or shell-like structures. The floor system that we are considering is made of clay blocks and reinforced concrete beams. It could present a concrete overlay with or without a welded wire mesh, or it could be without a concrete overlay. Also, like in the right-hand side, without the concrete overlay, the floor can still carry some horizontal load transfer system. And this mainly happens thanks to the development of compression arches in the floor spans that could be like transfer thanks to these floor units. But what happens after a seismic retrofit? If we want to take like the challenge to avoid inhabitant relocation and we are forcing the retrofit from the outside, we will provide external shear walls or exoskeletons. In that case, we are providing like a stiffer elements outside of the building. And so we are forcing like this force load path of arches to increase in size and also like to increase like in load transfer. So in this case, the load transfer increase, the compression in these arches, so these are compression arches, will increase and could like trigger failure of these blocks. We consider specifically blocks without the concrete overlay, which are seen as like the more like, let's say, fragile. This arch mechanism could like develop in the in-plane even without a reinforced concrete overlay. Specifically, there are three possible sources of failure of this mechanism. One is associated to the high compression load transverse to the blocks that we have like the arch key section, so the point A. The other one is the failure at the tied arch support, usually a failure like in shear that we have like close to the support, which is the point B, or we could have like the failure at the tie in tension. Among like these this failure mechanism B is the most probable. So to study like this mechanism, an experimental campaign was carried out And it started back to 2014, starting by testing the single units, the single clay block units in shear, and finding like an estimated shear stress capacity of about like 1.6, 1.9 megapascal. Then in 2021, we had like the chance to test like in this situation of these systems in a real condition, in a floor that needed to be demolished. So we managed like to test like two specimens with and without a concrete overlay. And in the case of concrete overlay, it was like 1.5 centimeter of concrete with no rebars. So without the concrete overlay, we observe like a rigid load distribution among the clay blocks with like a brittle, fragile failure at the internal webs. In the case of concrete overlay, we saw that the concrete struts in the overlay took most of the load. In both cases, the failure was very fragile and brittle. Then we managed also like to do some tests on a longer elements in a 3-meter length floor specimen, which was like specifically designed to study the diffusion problem, stress diffusion issue that could arise at the concentration of external shear walls. So based on this research, it was possible to say that the primary concern was related to the ultimate capacity rather than the diaphragm deformability. So these systems are rigid and fragile. So finally, we managed to test all diaphragm resembling like real, almost like real conditions. So this was made possible by the DCAB test program, which involved like several universities and also like companies. And it was possible thanks to the financement of the European Commission. So here you can see like some drawings of the test specimen, which is like about like 9.2 meters times 3.9. And it consisted of 3 spans with like eight position of possible columns with like clay blocks without concrete overlay. So the columns were not built, but instead in the position of the columns, some supports were provided, supports that allowed all the possible displacement of those points. The test was tested, the specimen was tested with 2 actuators with like load and unload cycles, not without a reversal cycle, so only one direction loading and unloading. And the beam supports were designed to be simple supported. So on the one side, there was like a detail resembling a hinge, and on the other side, a detail resembling like a roller. Here is how the specimen looked like before the test. You can see like the 2 actuators in the middle of the top of this figure. Here you can see the preliminary results. We are still on the process of post-processing all these results. The test was carried out last December. So the first point is representative of the actual floor capacity. So we can see that we have like a very stiff behavior until reaching like the capacity. And when I talk about capacity, I talk about the activation of the mechanism B and the failure of the shear transfer at the support. Then, thanks to some details, in particular to the provision of some additional rebars in the course, which could like simulate like a steel string course around the floor, This detail triggered the activation of the reinforced concrete tie and the development of another mechanism. But the capacity of the existing buildings should be like considered the first one at about like 170 kilonewton in this case, that is compatible with the shear stresses capacity that I indicated before. Here you can see like the damage pattern at the capacity. So you see that all the damage is lumped at the across like this close position of the supports on both the left and right hand side. And you can see like all the failure of the cracks developing the edges of the blocks. Then, thanks to the provision of this additional reinforcement in the lower court beam, the arch mechanism could like started to lowering down and engaging in tension the reinforced concrete tie. In the project was part also like a firm, the Asda Engineering, which developed a finite element, very refined model through the software STKO implementing like OpenSeas. In this case, it was possible to model the whole diaphragm with the boundary condition and imposed load. The elements were three-dimensional elements for the reinforced concrete beams, and also rebars were embedded inside of the beams. And the clay blocks were modeled with like a shell elements. Here you can see like some preliminary results where you can see in continuous line the finite element model results up to that point of the capacity that I was mentioning before. And with the red circles, you see like the experimental test results. So you see that we have like a good like modeling of the capacity. So the purpose of this research was and on the implementation of this finite element model is like to define let's say a good modeling strategy to assess different type of condition. In particular, in the case like of opening of different diaphragm configurations to derive some design indication for professional engineers. Here you can see like the damage pattern recorded from the finite element modeling. So you can see like the development of the failure at the support, and also like the some cracks in the beam cord. Now let's talk about the input loads for the diaphragms. So response spectrum analysis generally not appropriate to obtain the forces in the diaphragm. It's okay for the maximal loads, but not for defining like the load path. This is also due to the fact that response spectrum analysis implements combination rules that will make like the mode shape acting together and will cancel the sign of the contribution of each mode. So internal forces in diaphragm must match the forces at the lateral force resistance element, so it should be like in equilibrium. So building codes, in the building codes you could find some indication on how to derive the loads in the diaphragm, and so design like the diaphragm. In particular, in the New Zealand building code, they suggest to use like a pseudo-equivalent static analysis, and similar consideration are available in the USA. So basically, in addition to the traditional equivalent static analysis, let's say a triangular load distribution, which is good and used to derive the forces for the vertical element design. There are additional forces, these like equivalent, pseudo-equivalent forces that are used like for the diaphragm design. So basically, this methodology will consider an overstrength factor associated with the equivalent static analysis, and this will provide the right inertia in the upper floors. Then in the lower floors, there will be like a cutoff limit associated with the PGA. At the lower stories, like the PGA value will represent more likely the inertial loads, and also this was like observed in the test carried out in San Diego. So with these like forces, we will end out with the right deformed shape, and so with good transfer forces. One other approach, which is like indicated in US, is based like on applying the diaphragm design forces at the diaphragm level that you want to design, and on the other level to apply the lateral forces resulting from the equivalent static analysis. So basically, we are mixing the two loads. The diaphragm forces that is indicated as FPX are used like to derive the inertial loads inside the diaphragm. These inertial loads need to be in equilibrium with the loads that are transferred to the vertical elements of the lateral force resisting system. So basically what you do from the previous like load distribution, you find the shear action inside all the elements of the lateral force resisting system and of all the vertical elements. And if you like make like the difference between this shear load, the shear internal action at the store for each element at the story above the story that the floor diaphragm you want to design, and below, that difference is the load that is transferred to from the diaphragm to this element. So you have like the whole floor, you have like the inertia loads on the floor, and you have like these loads that are like let's say, that need to be in equilibrium at the vertical elements of the lateral force resisting system. And with those like forces, inertia and these like story force, you can define load path and design your whole diaphragm. So now let's have a look on the forthcoming edition of the Eurocode 8 regarding the design of structures for earthquake resistance. So in the new edition, there will be like the definition of the different elements of the diaphragm, like the cord, the collector. There is like a particular indication of considering the load path continuity, which is like important to ensure that both like the vertical load and the diaphragm, vertical load resisting system and the diaphragm are acting together in resisting the horizontal actions. And also there is like indication related to how to consider the diaphragm rigid or not. And I remember that this consideration is based on, is required in the case of diaphragm, rigid diaphragm, you can lump the masses and the moments of inertia, mass moment of inertia at the center of gravity of each floor, and this will like simplify the analysis of the loads on the lateral of the vertical elements of the lateral force resisting systems. So there are like indication on where to consider a rigid diaphragm in the case of different structural typologies. Unfortunately, there is like no mention of the beam and clay block flooring system. For instance, in the case of precast elements, a diaphragm may be taken and considered rigid if like the horizontal displacement do not exceed by more than 10% the same displacement in the case of rigid diaphragm assumption. Another important indication that we find like in this forthcoming edition of the Eurocode 8, and we will see the final version when it will be out, and if it has been like implemented as I show you, will be like to include some overstrength requirements in the case of the design of diaphragms. Particularly in Eurocode 8, there is no consideration about, as I show you, like in the DSDM project, to consider like plasticization of the diaphragm. The diaphragm is not considered, is not allowed to be damaged like plastically in the case of the design earthquake. So there is an introduction of overstrain factor that will be different in the case of failure, diaphragm failure mode in shear, so fragile, or in bending, so like ductile. And this is like divided by the different design classes that are considered in Eurocode 8. There are 3 design classes. So this overstrength should consider also like the behavior factor. In the forthcoming edition of the Eurocode A, the behavior factor is made by 3 components. There will be like a component due to overstrength associated with redistribution of action, which is called QR, an overstrength from all other sources, that's QS, and an overstrength related to the deformation capacity and energy dissipation. So basically, when we do like the design, we obtain FB from our, let's say, response spectrum analysis. If you take like a FB for the design, you need to consider that there are sources of overstrength. And so the design load should be FB times QR times QS. If we consider the additional overstrength factor gamma D that I showed in the previous slide, the amplification required for the diaphragm design should be QR times QS times gamma D. So basically, there is like a hierarchy of resistance to ensures that the diaphragm does not fail before the primary vertical seismic resistive elements, so maintaining like structural integrity. So as you see, there is like no mention as like in the New Zealand code and the US code about the use of equivalent static loads. There is no that the same consideration that I mentioned before related to the relevance and the appropriateness of this type of analysis are not considered. And this is a kind of like actual limitation of the building code. So a good way to define and obtain the design load for the diaphragm should be like to follow the static analysis that I mentioned before. In that case, you can find like the right inertia forces and the right transfer forces. So I rushed a bit, I see. So here I provide you some like references where I took most of the elements of this presentation. So related to building codes, existing building codes, existing research, particularly research of Bull in Gardiner in New Zealand. and also like some other references related to these beam and clay block floor systems that I mentioned before. So I hope you enjoy like this presentation, and I invite you to visit us in Bergamo sooner or later.
Thank you, Andrea. It was very interesting, at least for me. So I now open a discussion. So any questions from the audience? Yeah, like usually. So I'll start. I'll start with the discussion. So based on what you said, I have a feeling that the better times are ahead of us. So in terms of taking into account the let's say phenomena which are related to the diaphragms and the of course the issues which are consequences. So the new generation of codes will bring us closer to, let's say, the truth at some point, but we still have a lot of work to do. So do you think that besides the experimental results, maybe some, let's say, data from the field, from the buildings which are occupied or which have been, let's say, slightly or more damaged during earthquakes, can we also use that based on are there some options to, let's say, if we have some photos or some measured, let's say, quantities like accelerations, can we make a rough estimation of what happened to the diaphragm and what is its state at that particular moment? Should it be retrofitted or can we just leave it like this?
Yes, like so thank you. This is like an interesting question. So basically, in this, if I consider, let's say, the continuous lab system, that is quite like we are at quite a good level of development of design and methodology, and also like finite element modeling, or like simplify the modeling, like strata and tie, grid large model, or stringer and panel system. So these are like a kind of like available. In the case of like of beam and clay block systems, we have not. And it's not possible to infer like let's say and look at the damage in existing buildings made of the like this system, because usually in these existing buildings designed for gravity loading, we have like a failure of the lateral force resisting elements before failure of these diaphragms. And also like this, as I tried to mention like before, in the case of existing buildings where we have like these, like let's say we have just gravity columns, you will have the development of these small arches, and these small arches are sustainable by the diaphragm in terms of like load and capacity. The issues arises when you have like a stiffening of the let's say the edges of the building, and you don't want to retrofit the diaphragm to improve, to strengthen the diaphragm, because if you need to strengthen the diaphragm, you most likely need to make like the inhabitants to relocate. So going back to your question, we don't have like observation of like damage in this kind of like floors because something was damaged before them.
Or the
But this
diaphragm
could
is
happen after retrofit of the if you retrofit only the lateral force resisting system, the vertical elements, you may like trigger damage in the diaphragm. So what you can do is like to derive like the capacity also like of existing diaphragms with these systems. You can derive the capacity of this arch shape mechanism and see which is like the allowable span between consecutive, let's say, shear walls.
yes, I understand. Thank you. It makes sense, but I'm always wondering, if I got you right, we should keep the things balanced. We cannot strengthen one part of the building too much after an earthquake and then just leave the other ones, or vice versa. So we can make more problems than solutions at that
Yes, no,
point.
but it's possible to, let's say, to strengthen like existing this kind of system. Also, like you can act from above with like additional topping, but that you need to remove the finishing. You can act from below, from the introducts, so you can provide, let's say, a bracing system, or you can act from the outside, like Professor Marini in our group proposed like to use like an external diaphragm. So in corresponds to the balconies, you can provide like external diaphragm that can carry the inertial loads.
Yeah, and then the people don't have to move out during the construction work
This is like
in
our
general.
purpose.
Yes, great, thanks. So we have some more questions. Professor Burza, please.
Okay, hello. First of all, thank you very much for a very interesting and very important lecture. I believe that the topic of diaphragm is not being well covered. I would say even at universities that I know of, very often it's very, I would say, low profile topic, and also in the books on earthquake engineering, there's very little coverage, just in a few books. So. But my particular interest is in this system. I call it composite clay and the concrete system, and we have it here in Serbia and in the whole region. In fact, it's a very popular system for low-rise buildings, and I was not aware that it exists in Italy until a few years ago. We had a joint project, seismic, with I think it was run by University of Bologna, and then all countries in the region were sharing what kind of systems they have, and that system is very popular. So this is the first time I see testing on that system which you have done, and I have. It's very encouraging to see the good simulation, numerical simulation of the behavior of the system, and I'm wondering. I have a question: how was it simulated? How was the effect of concrete? You mentioned reinforcement was mentioned, but were there special elements that simulated the effect of concrete and the possibility to allow for possibility of, let's say, relative movement, or the type of failure that happens along that path, or not? It is not clear. It's clear that about clay elements, but it was not clear if there were any special modeling
Yeah.
feature. Mhm.
Okay, no, thank you very much for the question. Yes, like just one thing before answering directly to your question is related to the first part of your on what you were saying. So the focus seems that in our course is more like on the rigid and the flexibility of the
Yes.
diaphragm, more than provide like the right demand and the
Mhm.
right capacity models.
Mhm.
So that's one step that we need to take in the future. So regarding like the model, so
Mhm.
the clay elements were modeled like as like a brittle material, and they were modeled each of them like separate elements with like contact friction elements, surface elements, line elements between them. And regarding like the concrete, it was used like um, a specific hysteretic rule developed by ASDA and implemented in OpenSeas that is somehow related to, let's say, could manage like damage in let's say in tension and defining like the let's say a smear the crack approach with like energy fracture energy for tension. And rebars were made like as fiber elements inside and were embedded inside the three-dimensional elements of the concrete. But they were like a model as fiber elements, but acting only in tension. So basically, with few fibers, with not taking like the bending capacity of the rebars. Then, like as boundary condition, they were like ideal boundary conditions. So the roller and the hinge were boundary elements in just localized, and we made like some steel plates, the simulation of some steel plates to like make some diffusion of the loads from the actuator to the beams. I don't know if I answered.
No, you answered. It's good. It's clear. Thank you. And I'm wondering in your test and your experiment, or maybe in future. I'm not sure if you're planning future experiments because, as I say, it's very important. If you already started, that's very limited evidence on that. Are you planning to do some, or I believe there was no topping, there was no reinforced concrete layer on top of it because you wanted to simulate the status of the older, let's say, diaphragms. But I'm wondering if you were considering, like, sometimes it's nice to do even the test after some damage and, imply this retrofit and see what would be the improvement of the system. So, are you planning to do it because that topping is a solution, or not solution? It is a part of should be a part of construction practice nowadays. But it would be interesting to see the difference between the two. Of course,
Yes,
is
yes, for sure. So that was the initial plan. The initial plan was to test like two specimens, one without concrete overlay and one with concrete overlay, and to test like in a cyclic, like not like a load and unload. But where it was like not possible for like let's say budgetary issues. So we started with like the let's say what we thought it was like the most vulnerable of the situation. So we started with that one. It will be good to do some tests with concrete overlay. We did with concrete overlay in the small specimen that I mentioned. But what we can do is when we will have like finalized the finite element models, we could like use like the, let's say, the tuned material finite element models to test different situations like diaphragm with openings, large openings on eccentric openings, or different stiffness of of the shear walls or the exoskeleton, and also providing like a topping like layer. So this is like I think we will do like the finite element simulation before doing the test.
okay. Thank you. And are you going to publish or are you already publishing the results of this? I have not seen personally, but you mentioned some references of the test that you shared
So
with.
we publish I have like in the
Which you
reference.
showed in the references.
The
Yeah, okay, took a
reference,
note of that.
let's
Mm-hmm.
see. So this one, the third last one, is related to like some consideration
Oh,
that
okay.
we made
Mm-hmm.
on this arch mechanism.
Mm-hmm. Okay.
And in that case, we model with like a homogeneous, with let's say equivalent damage, concrete damage plasticity model to capture the shear capacity of these blocks. And that was also good to define like and visualize like these arches and like these mechanisms. Of course, we will publish the results of these tests. We will have like some conference preliminary results, like in the next FIB in Lisbon, and in the areas project in May. And yes, there is a lot of data that we need to process.
It's definitely worth publishing. I don't want to take more time since I see that there are some other questions. Thank you very much once
Thank
again
you, thank
for
you,
giving this lecture to our members.
thank you.
Thank you. Before we go to the chat questions, Professor Stojadinovic has raised raise the hand.
Okay, yes, we'll go to the chat. I'll try to be short. Thank you very much for a good talk. I have two questions. The model that's developed by SDEA is essentially an OpenSeas model, so it's publicly available, I hope. I hope also it's modifiable to account for, like you said, openings, very important. And another one, as you will see in the chat, timber with overlays, very, very common also. But what I want to ask is the model available? How will it be distributed, and will it be changeable? That's one question. And the other one is a little bit more complicated and perhaps more special, so you don't have to answer. It has to do with the elongation of the beams and the pushing out of the columns. That one is quite complicated. And if you can tell us if you know how this could be captured in models or even code. But let's first talk about the modeling of the diaphragms and open seas. Thank you.
Yes, thank you. So right now, so the model we are using like internally, I don't know. I think somehow in the future when we will have done like some the all like the consideration and publish, I don't see like restraints to distribute it. I think it will be like good for the research community to work on that and improve improve that. So right now it's not available right away. Regarding like the elongation, yes, this is a good question. I think like in this like in this model we couldn't see because it was not like subjected to this. So the diaphragm failed before like reaching any like plastic hinges in the elements. So yeah, I think it's possible like to with the same model in the case of modeling like how you say like a moment resisting frame and embedding like this model that the refined 3D model. I think it could be possible to capture it, and I think it's a very good question and a good point to see what happens in this system in the case of beam elongation. I see that the indication in New Zealand, they say that it could be about like 3.5% of the beam depth, and which is like quite a lot, and could like tear apart the mesh or the starter bars in the topping, also in the existing in new buildings. So it should be accounted for. Yeah, sorry
Yeah.
if I.
No, I agree. About the elongation. And I think it's quite large when we test solitary beam column elements. The New Zealand estimates are not that wrong. However, if that was actually happening in the building, we would probably see a lot of this. My expectation is that a lot of that elongation is restrained by the floor slabs that are more competent than the ones that we have, and the interaction between the edge beams or the beams of the moment frame and the floor slabs
Sure.
is complex to understate the situation. Exactly what goes on there we don't understand, and that's why I'm looking forward to the model of the diaphragm, that at least letting people get a little bit further away from the tension compression cord model that we have now.
Yes, yes.
Thank you.
Thank you, Professor. We have a couple of more questions in the chat, so I can read them out loud. The first one is, what do you propose regarding modeling of timber floor diaphragms? Does any existing timber floor needs to be strengthened with concrete topping to transfer the horizontal load?
So that one, so we didn't cover like timber diaphragms. Let's say in existing historic buildings, there are like some solutions to provide like let's say stiffening of existing timber diaphragms by providing additional layer also like of timber. Yes, timber, I don't say, yeah, sheet elements. And that's like one solution. in the past, we made like some tests also like to not myself, Professor Marini, to transfer to provide like a concrete or high capacity concrete layer above the timber floor and make like some connections with dowel connection to the beam elements of these timber floors. But yeah, I don't know what to say in addition. I'm not an expert about it.
No, thank you, because it's a tricky question because we have a lot of these timber floors, and actually one of my PhD students was doing that research. So basically, in short, he gave some thoughts about let's say coupling of the concrete topping with the timber floor via let's say nails, bolts, and stuff like this. It's very tricky because the shear is very complicated in these connections. So thank you, of course, for the answer. And from the same participant, the other question is there any option for small scale statical test environment in laboratory for simulating dynamic behavior?
No, that one, it will be good, but not
Yes.
in small scale. At the beginning, we were thinking about like using like because like these areas project involve like different testing facilities. Some of those had also like shake tables. Also like in New Center in Pavia, we have like also one a big one in Bergamo in Ismes. But the point is that like to do like a small scale we need to place for like a similitude law, we need to put like additional masses. And so it was getting like very complicated because the masses acting on the top was not good because it will alter like the stress flow. And so we made it like as we did. Yes,
Yes, I
if you have like
agree.
a big facility like the external shake table like in San Diego, that could be an option, but
Yes, I
probably not.
completely agree because the small scales, the simulated laws are complicated as they are, in timber or any other stuff related to the experiments of this kind of phenomenon. It can be very, very complicated to,
Yes.
to properly simulate.
It's very interesting. I would love to do those tests. I would love really.
Yes, to have a home based, small scale facility would be perfect. And another, I think it's the last chat question, is what kind of seismic design approach would you recommend for flexible diaphragms?
Now, in the case like of flexible diaphragm, you will have like that the um, that the load will be distributed, let's say, half away in the let's say in the lateral force resisting elements of the span. But it also like if it's flexible and if you don't let's say the fact that it's flexible it means that you cannot like lump
Yes.
the all the mass and all the inertia in one point. It means that you have like to consider distributed. So if we follow, let's say the equivalent static analysis approach, we can obtain the inertial loads in the diaphragm, also if it's flexible,
Mm.
because we need to model it. And we can, with those forces, we can define load path and we can define like the design. So in that case, it depends like on the material type. You can, as I said, it's possible to use like strut and tie models to the grillage model made like in New Zealand that was like for concrete slab, or like recently Professor Estrepo in California applied the stringer and panel model for reinforced concrete slab, but could be applied for other type of like diaphragms. So I suggest like to define like the loads, the approach that I mentioned before. And to design, that's it depends, but it's possible to follow either like strut and try, grillage, or stringer and panel models. The deep beam, let's say approximation, it doesn't work always, because it works well if you have, like, let's say, simple supported conditions. You have like shear walls with like the same, like, length, and so same stiffness, equally spanning like all around. But if you have like a complex geometry, it's not working anymore. So you need to go farther with, like, let's say, strut and tie. Let's say maybe the simplest is the strut and tie approach.
Yes, there's no closed form solution for this one because it's very complicated in any case, especially with the existing structures, which already have some probable damage which happened at some point, and then you're like fishing in the dark. So basically, it's some situations. Okay, thank you. So since the time is now almost 5:10, do we have any more questions for the discussion? Okay, I guess not. Dear Andrea, thank you very much. It was very inspiring, and I really enjoyed both your presentation and the discussion part. And I hope you enjoyed it too. So
Yeah.
we really welcome. We're really looking forward to welcome you once to Serbia when there's a good opportunity.
Yeah, it will be a pleasure. So thank you again for, like, the invitation, and also thanks to all, like, the researcher that I mentioned, and also the one in the references that made a lot of, like, the dirt work, and that I tried to compact and present to you.
Of course, great, perfect. So thanks everyone. Have a nice day, and let's see you another time. Bye bye, ciao.
Bye bye. Ciao, arrivederci.